Okay, hello everyone. Uh, I hope you started a great day this week. And starting from this session, we are gonna solve some example to kind of like practice what we learned so far about the Laplace transform and transfer function. So we wanted to like kind of uh, stabilize that knowledge in our head. So by practicing, we can make sure that we are fluent on how we run the Laplace transform and how we can find the transfer function of any system. Now, before I start, is there any question regarding the previous sessions about Laplace transform and transfer function, what we discussed before? No? Okay, let's just start. The first example that we are going to see, yeah, okay. Yeah. Uh, would you repeat two questions? Okay. Yes, you are using the normal case. Yeah, okay. Yeah, sure. Okay. Is there any other question? No? Okay. The first example that we are going to see is a very simple one that we wanted to like calculate the Laplace transform of the simple ut, the step function. Okay. Now, we said the Laplace transform is going to be from zero, the integral is from zero to infinity. So when we have an input as ut, meaning a step function, from 0 to infinity, the value is 1. Okay, so we can simply, instead of ut here, we replace that with the value 1. Come on. Okay, so that's why you can see that is eliminated. Ut is eliminated. That's actually because uh, we don't have any kind of like other function when we talk about the step function from 0 to infinity. Now, when we want to like calculate the integral, okay, or solve the integral, we have to get an integral over the e to the power of minus st from 0 to infinity. We know that the integral of e to the power of minus st is minus 1 over s e to the power of minus st, and we wanted to like run the integral from 0 to infinity. So if we put infinity as for the t, so t goes to infinity, this one becomes 0. So it becomes 0 minus, if it's 0, if t goes to 0, the exponential goes to 1. So it's going to be minus 1 over s. These two minus cancel out each other. So we are going to have the Laplace transform of 1 over s. Are we good? Now, you can see that the real part of s is considered as positive. Anyone can, based on the physical example that we solved and discussed in previous session, anyone can say, first of all, what is the real part of s and why we consider it as positive. First question, what is the real part of s? Anyone can remind us about the concept? We said S is alpha plus J beta or omega, whatever. Okay, so this is the real part. Physically, what is that real part? You remember the mechanical and electrical system that we solved?
For electrical would be actual impedance. The real
The impedance also have the imaginary part. The impedance is like resistor plus j omega, either L or 1 over C. Okay, so we have imaginary component in the impedance. What is actually, like, look at this impedance. The real part is R.
Yeah.
What is that R? Is the resistance, right? What the resistance do? Resist to the current flow is a damping factor, right? So when we say the real part is positive, we mean that we have this Laplace transform considering the damping factor is positive, which is very kind of like a logical assumption when we talk about a physical system. We don't have basically negative friction. We don't have negative damping. It's not damping anymore if it's negative. Are we good? Now, let's move on to the next example. What if our input is TUT? First of all, when we say TUT, another name for this function is ramp because it's increased linearly as time goes by. Are we good? Now, how we can calculate the Laplace transform of this input? Again, the definition is the integral of that input times e to the power of minus st dt from 0 to infinity. Now, here you have two function multiplied by each other. Are you good? So what happens is that you can define these two function, one as u, the other one as dv. And we use the rule for integral of u dv, which the integral of u dv is going to be uv minus v du. This is the property of the integral. Now, if u is t, that means du over dt is 1. Are we good? And if dv is e to the minus e to the power of minus st dt, that means v is minus 1 over s e to the power of minus st. Are we good? So this term become t times e to the power of minus st over s. There's a minus here too, from 0 to infinity, minus the integral of v is 1 over s can goes outside of because integral is over t, e to the power of minus st, and du is 1 dt. Are we good? Now, what is that? This is the 1 over s times 1 over s. We already calculate that in the previous session. So this part is basically 1 over s squared. How about this one? When t goes to infinity, this term becomes 0, so it's 0. When t goes to 0, this one becomes 0, so again it's 0. So this part is always 0. Like, not always. The boundaries are 0. Are we good? So what is remaining? 1 over s squared.
-1 over s.
No, the integral of e to the power of minus st is minus s. Okay, so this minus cancel each other out. Are we good? So, any question? How about if we wanted to like calculate the Laplace of sine of 3t? Okay, with the characteristics using the table, you already know that if we have sine of omega t, that means it's omega over s squared plus omega squared. Okay, but let's actually practice how to drive an integral. Actually, this one is a very good example for you to actually work on your skill on getting integral over the function. Now, here again, we use the characteristics of integral for multiplication of the like u dv. So we call this one u and this part dv. Ergo, du become 3 cosine of 3t, and v become minus e to the power of minus st over s. Are we good? Now, again, we know that this integral is going to be the integral of u dv is going to be uv minus integral of v du. Okay? So what's happening? uv is going to be sine of let's call this one is because I need that. So is going to be sine of 3t times e to the power of minus st. There is a minus here. S from 0 to infinity. Minus, here we have minus over s on v, so it's going to be plus 1 over s. We have a 3 here too, so we are going to get it outside of the integral. We are going to have cosine of 3t e to the power of minus st dt. Are we good? Now, let's call this one IC, I of cosine. If we call that, you see that is is 3 to the 3 over s times IC. Now let's calculate IC because we have another integral to solve. Now I eliminated this one. It's the same. If we calculate for infinity and 0, both of them are going to be in infinity this term is 0, in 0 this term is 0. So this one is always like is it not always. It's going to be 0 minus 0, so 0. Are we good? So now let's calculate the IC. IC, again using the UDV rule, would become cosine of 3t, it's actually minus, over s, okay, times e to the power of minus st, minus 3 over s. There is the cosine integral is going to be the cosine differential is going to be minus sign, so it's become plus sine of 3t e to the power of minus st dt. See what happened? We already have this. This is is. And if we go from 0 to infinity, for infinity is 0, so this one becomes 0, minus minus is plus. When we go to the 0, this is 1, this is also 1, so it's, what happened here is 1 over s. So the whole IC become 1 over s plus 3 over s times is. Are we good? Are we good so far? Now, so if we solve for is is gonna be let's solve for IC. IC is gonna be, we have that. Why I'm solving that? We have IC and we know is is 3 over s IC. Okay, so basically I of s is gonna be 3 over s times 1 over s plus 3 over s is. Are we good? So this one become 3 over s square plus 9 over s square. Okay? is, is. We bring that one over there. So there should be a minus here. Well, it's okay. So if we this should be a minus. I think I missed a minus. Yeah, the differential of the cosine is plus sign, is not minus sign, so it's minus. So if we bring it that to the other way and multiply everything by S2 is going to be S2 plus 9 times IS equal to 3. So IS become 3 over S2 plus 9. The same formula that we have. Do you see the derivation? So if you don't remember the characteristic of the Laplace, you can actually derive the integral and solve for the Laplace. Is that clear? Any question about that? Now, same derivation goes if we have a cosine. It's just a sine and cosine in the whole derivation would swap places. And we know that if we run that, we are going to reach to the part that it's going to be S over S squared plus 25. If you run the derivation, which I encourage you to do that, same derivation. The result is going to be S over S squared plus whatever omega you have here is squared. Are we good? What if we have a derivative as our, like a differential of a function as our input? So x of t is going to be v prime or v dot of t. And we also have an initial condition, remember. Okay, when we have a differential, we need an initial condition. Now, from the characteristics, we know that the Laplace of the v dot is going to be s vs minus the initial condition, the initial value, which is here is going to be s vs minus 2. Now, again, let's have fun and actually run the integral. Our integral is going to be the x of s is going to be the integral of v dot e to the power of minus st dt from 0 to infinity. Here, now, we consider this one as u and this one as dv. Using the same characteristics, we have, like in this case, the du is going to be minus s to the power of minus st. Are we good? And the v is going to be simply v of t. So what happened is that the Laplace transform of x become uv, which is v of t times, this is minus s to the s times e to the power of minus st from 0 to infinity, minus the integral of v t. Sorry? This minus came from here. Did I? Yeah. Oh, no. Yeah, you are right. There is no minus. Yeah, you're right. Thank you. So this is u, this is v. So it's going to be vt times e to the power of minus st. My bad. So, and the v du is going to be plus s e to the power of minus st. Are we good on that? Do you know where that came from? Now, this one If goes to infinity, it's 0. If goes to 0, it's minus v of 0. Are we good? Plus, now this one is the definition of the Laplace of Vs. So that is the Vt, which is S V of S. So we reach the same equation. Is that clear? Are we good on how we reach the end result? Any question? I don't want it to like have any confusion. Okay. Now, what about if our x is an integral of some function? We already know that from the characteristics, the integral is going to be if the x is integral of v tau d tau from 0 to t, the Laplace of x is going to be Laplace of v over s. Let's have fun and actually calculate that. X of s is going to be the integral of v tau d tau from 0 to t times e to the power of minus st dt, 0 to infinity. Okay, now let's look at the parameters that we have. We have t and tau, and the boundary is 0 to infinity. So the lower boundary is 0, the higher boundary is infinity. Okay, and the tau changes from 0 to t, and t changes from tau to infinity. We already mentioned that we have some theory named Fubini that we could swap the parameters in an integral when we have double integral. Okay, so we can change this and say it's the integral of 0 to infinity, integral of, what is that I want to write? E to the power of minus st dt. T goes from tau to infinity. And then we have v of tau d tau. Are we good so far? Now, what is that? If you run the integral, this one become 1 over s minus 1 over s e to the power of minus s tau. Are we good? Now it's from tau to infinity. If you do that, the infinity is going to be 0. The 0 is going to be 1 over s, so this minus would be canceled out basically. Now, here we have v tau. So this one become v of tau e to the power of, this is from tau to infinity, e to the power of minus s tau over s d tau. You can bring the s outside, and this one is the definition of Vs. So we reached to our expected result. Is that clear what we done?
It's kind of hard to like follow your steps on the board. Like the writing is kind of hard to understand.
Well, yeah. Let me explain what happened. Okay, we have a double integral. Okay, we have a double integral. One goes from 0 to infinity. Inside that, we have integral of v tau d tau from 0 to t. Okay, and we wanted to like calculate the Laplace of this, so it would be multiplied by e to the power of minus st dt. Are we good so far? Now, we use Fubini to swap the place of vt and e to the power of minus sd and swap the element. That's the parameters, tau and t. If you want to do that, we use the boundary conditions that we have. We know that the ultimate lower and higher boundary is 0 to infinity. And based on this definition, tau goes from 0 to t. So this is the boundaries of each of the parameters. Tau goes from 0 to t, and t goes from tau to infinity. Are we good? Now, if we want to use Fubini, the uh, 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 the main integral, the first integral remained the same. Okay, we wanted to swap e to the power of minus sd dt from v tau d tau. Okay, so we bring these two into the second integral here and bring these two outside of that second integral. Now, since we change the parameters, we have to change the interval, the upper and lower boundary. So we know that the t goes from tau to infinity, so the integral is going to be from tau to infinity. Is that clear so far? Now, we run an integral over this part. We solve this integral. The integral from tau to infinity of e to the power of minus st dt is going to be minus 1 over s e to the power of minus st from tau to infinity. Right? If we limit the t to the infinity, this becomes 0. So it's 0 minus, if we go to the tau, it's become e to the power of minus s tau over s, and we have another minus here, so it's going to be plus e to the power of minus s tau over s. Are we good? Now we replace this one here. So we have an integral of e to the power of minus s tau over s times v tau d tau. Okay? This s doesn't rely on tau, so we can bring it out of the integral. So 1 over s integral of v tau e to the power of minus s tau d tau. Now, this is the definition of the Laplace of v tau. Are we good? So this becomes vs. So what is the end result? Vs over s, which we were expected from the table that we have. Is that clear now?
Mm.
I try to be more clear in the next slides. Okay. Now, what if we have more complex function, e to the power of minus 2t times this is in the power. It's e to the power of minus 2t sine of 4t. Okay? This one is better show the x of t. Now, we know that from the table, we know the Laplace of the sine of 4t is going to be 4 over s squared plus 4 squared, which is 16. Are we good? Now, that e to the power of minus 2t, we define it as a shift in s. So, because of that, s become s plus 2, and we replace that in the function, so the whole Laplace become s plus 2 squared plus 16, and the denominator is 4. Are we good? This is from yeah, go.
Yeah, have you released this set yet?
This one?
Yes.
No.
Are you going to?
Yes.
Okay.
I would. Now, let's again have fun and actually solve the integral of e to the power of minus 2t sine of 4t e to the power of minus st dt. Are we good? Now, 0 to infinity. These two can be mixed together. So what happened is that the x of s become the integral from 0 to infinity sine of 4t e to the power of minus s plus 2 t dt. Are we good? Let's call this one p. Okay, just to simplify. Now, we already solved before in, I think, the second or third example. We already see how we can run an integral of sine of e to the power of minus st dt. Now here is just, instead of s, we have p. I don't want to go through the whole kind of like long derivation of the integral, but you know how to do that. This is u dv, so it's become uv minus integral of v du, and solving the whole crazy derivation. Okay, going through the crazy derivation. Now, we know the Laplace of sine is going to be omega square over s, here is p square plus omega square. Correct? Now, we simply just replace the p with what we had before based on s, and it become omega square over s plus 2 square plus omega square. Are we good? Now, I don't want to derive the whole integral. You know how to derive this integral. We solved it before. Any question on that? No? Let's have a little bit more fun. Let's say we have a simple RC a circuit, which is a series of R and C. And we wanted to like see, this is V of input. And we wanted to consider the voltage across the capacitor as output. And we want to see what is the transfer function that relates output and input. Okay? Now, what we can do? We have two ways to solve that. One is a differential equation. So basically, you run the differential equation over this, like KVL over this loop. Another way, which is easier, we already done the KVL in the previous session, so I'm going to go for another approach. Now, since they are in series, we know that they share the current, both input, resistor, and capacitor, correct? So what is the current of the capacitor, the resistance? What is the current of resistance? The voltage across it divided by R, right? What is the voltage across it? Across the resistance? If you run a KVL, what is it going to be? No, I know. IR, how we can find IR is going to be VR over R. What is VR? V in minus V out, correct? So this one is going to be V in minus V out over R. How about the current of IC? What's the current of IC? Go ahead.
Over. For C.
No, the current of IC. C dV dt. The current of capacitor is C dV dt, right? So it's become C first differential of V out. Now these two are equal to each other. So V in minus V out over R is going to be equal to C V prime out. Correct? Now, do the kind of like simple algebraic derivation. We multiply by R, so this one become R. We eliminate this one, is RC. We move this one to the from left hand side to the right hand side. So V in become RC plus 1, okay, times V dot out. Run a Laplace from this. This one become, if you run a Laplace, this one become V in of S equal to the no, this one is not. No, sorry. This is V dot. So let's do the Laplace here. It's gonna be V of in S minus V out of S equal to RCS V out of S. Are we good? Now you can do the algebraic derivation and you find that V out over V in is actually 1 over RCS plus 1. So what we did is that we used the fact that the series components share the current. The current of the resistor is voltage in minus voltage out over R is simple KVL. Okay? And the current of the capacitor is C, the voltage across the differential of the voltage across it. These two are equal to each other. So we have V in minus V out equal to RC, the differential of V out. We run a Laplace over that. This one is the Laplace of V in. This one is simply Laplace of V out. And this one become RCS times Laplace of V out. And then we just simply move this one to the other side and solve for V out over V. Is that clear? Are we good? Any question? Let's move on to the next one. What if we have an RL circuit and we want to calculate the transfer function of the current versus the input? Okay, now if you run the KVL over this circuit, you simply see that V input is equal to the RI, let's use the lowercase, plus what is the current, what is the voltage across the inductor? It's L I prime, LdI dt, correct? So now you have your KVL function, get a Laplace. This one is simply become V in of S. This one, you are using the linearity characteristic of the Laplace, become R times I of S. And this is a differential, so it become L. This is L. S, I of S. Again, we want to solve for I over V in. So if you do the derivative, the simple algebraic derivative, you reach the transfer function that relates these two input and output. Are we good? Any question? No? Okay. What if we have an RLC circuit in series and we wanted to find the relation between voltage across the capacitor versus the input? Okay? Again, we can run a KVL, and the KVL in this circuit this is KVL, become input is going to be equal to the voltage across the R, which is RI, correct? Voltage across the L, which is L di over dt, and voltage across the C, which is 1 over C, the integral of I dt. Very good. Now, we want to get rid of this integral, so we get a differential for the whole equation. So this one become V in prime R I prime L I double prime plus 1 over C I. Very good. If we run a Laplace from that, this one become S within. This one become RS times I here. This one become LS square times I. Okay. And this one is simply become 1 over Ci. And now we can calculate the current here. We can calculate the current of capacitor versus VA. Are we good? Now, what we wanted was not the current versus VA. We wanted the voltage of C versus VA. Okay, but we know the voltage is 1 over C integral of I. So the relation between the voltage of the C is basically 1 over CS I. We have the I based on V in. We simply multiply that by 1 over CS, and now we have the transfer function for our output voltage of across the capacitor over input voltage. Is that clear how we reach the result? You want to explain? Yeah, okay. Now, we run a KVL. This is our KVL. V in minus Ri minus L di dt minus 1 over C integral of I dt. Are we good? Equal to 0. We bring all the minuses to the other side of equation. So V in become Ri plus L di dt plus 1 over C integral of I dt. Now, we get rid of this integral by getting a differential from the whole equation. So here we have V prime, which is dV over dt, equal to the R times I prime, okay, plus L I double prime, second differential, plus 1 over C, the differential of integral is simply I. We get a Laplace transform. We run a Laplace transform to this differential equation. V dot or V prime is going to be SVS for the Laplace, correct? So here we have SVS for input. What about this one? This one become RS times I of S, correct?
It's the first derivative.
Is first derivative.
Okay.
We said each derivatives in S domain means multiplication by S. Now the second derivative is going to be S squared times IS, and we have an L as a coefficient, so it's become L S squared times I in S domain. Are we clear? This one is a simple coefficient times the function, so it's become 1 over C times the Laplace of I. So now we have this equation that relates the current to the input voltage. But we didn't want the current to the input. We wanted the voltage across the capacitor to the voltage input. We have to replace the I with the voltage of the capacitor. Now the voltage of the capacitor is 1 over CS times I from this equation. The voltage of the capacitor is 1 over C integral of I of the capacitor dt. 1 over C is constant, so we have 1 over C here. And the Laplace of an integral is 1 over S times that function. So now we have Vc equal 1 over Cs Is. We replace that here. We find Is based on Vc. We replace that here. And now we have the formula that relates the voltage of the capacitor, which we define as output, versus the input. And just by that, we can calculate the transfer function as a ratio of the input and output. Is that clear now? Are you good? Now, what if we have an passive integrator? Anyone knows what is the passive integrator? What is the RC integrator circuit is? No? Okay. It's actually very simple. The RC integrator is simply series RC, a low pass filter, when you have V in here and V out across the RC. So the same as we solved before. This is the passive integrator. Okay, whatever you have in voltage here, you would have the integral of that as a voltage across the C. What is this? It's a low pass filter. I wanted to let you have some intuition of what we mean by integral. What the low pass filter does.
Allows low frequency.
Allows low frequency and no high frequency. If you have low frequency and high frequency, what is in respect to that low frequency, what you could consider the high frequency? This is your low frequency, and you have some high frequency over it. What you can call very simply that high frequency in respect to the low frequency. Noise variations. Correct? What the RC filter do is it cancel out the variation. How? How you can cancel out the variation over a function? Let's say you have, let me give you a simpler example. let's say you have a DC with some variation. How can get that DC from the variation? How you calculate that DC from that haphazard? You get average, correct? You average out the variations. So you have the main signal, correct? We already said that. What mathematical operator do the averaging? Integral. So low pass filter is an integrator. Eliminating the variations gives you the averaged signal. Are we good?
Yes.
Make sense? Okay. Now we already know how to solve the RC signal. We already solved that example. Okay, so you know how to find the V out versus V in. Now here, very simply, before we run the KVL, KCL, and we equal the current with each other, but I want you to look at it from different way. This is a series of two impedances. So basically, it's like that. You have an impedance ZR. You have impedance ZC. This is ground. Come on. This is V in, and here you have V out. What is it? What that circuit reminded you of? No. It's considered as just the impedance. What's this one? Voltage divider. What is the result of the voltage divider? It's V in, okay, times ZC over summation of the Z's. This is going to be V out. So V out over V in is going to be the coefficients of voltage divider. Now you replace the ZC and ZR with the impedance that we already know how to calculate in Laplace, in estimate. Are we good? What about the differentiator? What's the differentiator circuit? RC actually differentiator. How you can create an RC differentiator?
Is it?
Let me give you some intuition. What is the relation between V and I here at resistor? Is a linear relation between I and V, correct? So the I is proportional to V with a constant coefficient. Okay, so the differential of I is going to be again proportional to differential of V. Are we good? What about the capacitor? Current is a differential C dV over dt, correct? So the current here is proportional to V dot. Are we good? So VR is proportional to VC dot. So if you connect the input to the capacitor and you get output across the resistor, your voltage is going to be the differential of the input. Does that make sense? Are we good on that? You can simply run a KVL. This voltage here is going to be CV prime, okay? And this is going to be equal to R to the V over R. Okay, so V out is going to be the come on. The RC differential of VC. Correct? What is VC? RC V in minus V out. So if you solve for V out versus V in, you are going to have your transfer function. But here you can see that V out is proportional to the differential of our VC. Does that make sense? So when you want to have the differentiator, you have the same RC in series, but now the output is across the voltage across the R. Is that okay for you guys? Are we good on that? Okay, now why I am mentioning the integrator and differential, because if later on you wanted to like design a PID controller, now you know how to design a passive integral part and the differential part of that PID. Make sense? From the passive part, there is a way to design an active PID using op-amp, but from the passive function, using a passive component, now you know how to design a PID using R and C. Are we good? What about op-amp? Let's say we have inverting amplifier. Let's take a Laplace transform of this circuit and find out how we can find the transfer function of such a schematic. Now, from the op-amp in an inverting amplifier, we inject the input through a resistor to the inverting terminal of op-amp. We ground the non-inverting one, and we make a feedback from output to the inverting amplifier. Now, there are two ways to make a feedback. If you use a simple resistor, it's just a simple amplifier, non-inverting amplifier. If you use a capacitor, what was R series C? It was an integrator. So it became an integrator, active integrator. Very good. Now, if you do the voltage analysis here, since the non-inverting one is 0, and we know we have a high impedance inside the op-amp, that means we don't have any current. That means the inverting terminal have the same voltage as the non-inverting one. So if this one is 0, this one should be 0. Now, if that one is 0, what's happening to our circuit? It becomes voltage in R1. This is 0. Okay. Then, come on. we have R2, and we have our V out. So whatever current goes to the R1, same current goes to the R2. Are we good? So whatever we injecting here, there is no current here, so it goes here. If you run a KVL KCL, you would find that V out over V in is gonna be minus R2 over R on, because it's just a voltage divider. Are we good? Now, if that's the case, we don't have any S in our system, so the HS of our amplifier is simply a constant gain. Does that make sense? We don't have any T in our function here. So if we run a Laplace transform, it's a constant number. The Laplace of it is going to be the same constant number. Are we good? Okay. Now, if we have an integrator and run a KVL, what happened here is that CdV dt would kicks in. So the current here is going to be V in over R, and it's going to have the same current as capacitor, so it's going to be equal to V out C come on C dV out over dt. You run a Laplace, it's become V in over R equal to CS V out. We multiply by R, so it's RCS, okay? And then this is actually minus because we have a minus here. And then if you run a V out over V in, you would have minus 1 over RCS. Is that clear? How we run that analysis? The op-amp doesn't drain any current, so whatever current goes through the resistor is the same current goes through the capacitor. This voltage is 0, so the voltage across the capacitor is V out. Okay? Minus V out, actually. The voltage across the resistor is V in, because this one is 0. Okay? So if you put these two equal to each other and run a Laplace transform, you can find your transfer function relating the output and input. Are you good? Where are we? Oh, we have the law. Here's the law. Ideal integrator. We already solved that. Okay, then good. Let's do the reverse part. We have the Laplace. We wanted to like get the time domain. Okay? We already know, like if we have x of s as 5 over s times s plus 2, since we have two terms, two zeros in our denominator, we have to split them up, okay, the two terms. So we have to make it to have a term with s in a denominator and another term with s plus 2 in a denominator. So we split those terms. Okay, we know how to calculate the a and b. We already covered that. Okay, so if we calculate that, we would have 5 over 2s plus minus, which is minus, let's go, minus 5 over 2s plus 2. What is 1 over s? What function has the Laplace of 1 over s? Step function. So it's ut. 1 times ut. And since we are going from 0 to infinity, that ut becomes 1. Correct? So this one, the Laplace of this one is simply 5 over 2 times 1.
To the negative, e. No, okay.
What is it?
E to the negative 2t.
We are going to reach that. This one doesn't have any time shift. It's just 1 over s. Correct? This one, this term, is just a over s. So the Laplace inverse of it is going to be a times ut, and ut is 1, so it's become a. The other one is s plus 2. So we have a time shift here. We consider that as p. So now the Laplace inverse of b over p, what is going to be? Is going to be 1. Okay, and since we have plus 2, is going to be e to the power of its time, e to the power of minus 2. Do you remember that characteristics? Okay, time shift is to the power of minus 2. So it's become minus 5 over 2 times e to the power of minus 2t. Whatever we have here, minus that value times t, e to the power of minus 80. So this is going to be our time domain function for this Laplace input. Is that clear how we reach that? What if we have repeated poles, repeated zeros in our system, meaning one of the s's is squared or like cubes, okay? So it has power for it. Now, when you have such a system, when you want to like split the denominator, now you don't have to just need you shouldn't just consider s squared. You also have to consider s as the denominator when you split. So when you want to split these terms, it's going to be a over s plus b over s squared. So far, we deal with this one. Plus c over the other term. Are we good? When you have repeated poles, you need to consider all the derivative, all the powers up to that power you have. So if it's 3, you would have another factor of like s squared, and s cubed. Okay? Is that clear? Now, you know how to run the derivation to find a, b, and c. Okay? If you run that, you will find the values. When we have the values, actually, like I wanted to like go for a actual like formula a over b. A over s, we already know that is gonna be a times ut, so it's gonna be a, correct? What about b over s squared? What was 1 over s squared? It was t. So it's gonna be plus bt, correct? How about this one? C with a time shift, e to the power of minus 3t. Now in this equation, c becomes 0, so we lose this term, okay? And we have these two terms. You have to run the calculation, okay? So is that clear? What is we have complex conjugate poles? meaning one of the terms here has a conjugate. This one is basically s plus 2, s minus 2. You know what I'm talking. So this one, if it's this equal to 0, you would have two poles. Each of them are conjugate of each other. Is that clear? What we're talking about? S plus 2 squared equal to 0. If you solve that for s, the result would be two complex number. Both of them are conjugate of each other. So it's going to be, one of them is going to be alpha plus j beta. Another one is alpha minus j beta. Okay. Now, what about when we have this type of term? We basically, these are the s for this equation. We split them up to simplify the situation. Now, if you do the calculation, if you split them, if you simplify the equation in the denominator, you would have one simple square plus a constant. Now, what this one reminds us, we have a term with the s, a square plus another constant, a square, okay, in our denominator. You see this one? What this one reminded of you is a sign, and this one is has a 10 actually. What is the, if you consider this one as omega, what is the Laplace of sine of 3t? It's 1 over s squared. Sorry, it's 3 over s squared plus 3 to the power of 2, right? Now, we don't have this here. First of all, this one is 10, is not 3. And here we don't have s, is s plus 2. Now we have to deal with it. To make it correct, we need to change that 10, deal with that 10. So if we have the coefficient of 10 over 3, now our Laplace become 10 over s squared plus 3 squared instead of 3 over s squared plus 3 squared. Are we good so far? Any question about that? Now, again, another difference is that s is that time shift. So we need to also include some e to the minus 2t in our Laplace inverse. So what's happened is that we have a coefficient 10 over 3 e to the power of minus 2t because of the time shift, and the general function is sine of 3t. Do you get where I get here? How I get here? Are we good? Any question? No? Okay. This is for today because we already reached the time. And actually, the rest of example is the same, basically. So I will upload that. You can go over that. But we are also gonna have another example session for the Thursday, and next week we are gonna start talking about the a space state analysis, which is a time domain analysis. Any question? No? Okay. Have a good rest of the day.